A very warm welcome to one and all. I am Dr. Adeline Suji K, working as an assistant professor in the Department of Computer Applications, Bishop Weber College, Trichy. In this session, we are going to see about path planning and vision systems, which comes under the subject robotics and its applications of Unit 4. In Unit 4, Part 1 covers the path planning and the case studies in path planning. First, let us see what is path planning. Path planning in robotics refers to the process of determining an optimal path for a robot to move from a start position to a goal position while avoiding obstacles. And it is widely used in autonomous navigation, industrial automation, and intelligent transportation system. Now, let us see the key objectives of path planning. The various key objectives are: the first one is finding an efficient and collision-free path, minimizing time, energy, and computational cost, adapting to dynamic environment, ensuring smooth motion transitions. Now, we will see the overview of path planning methods. The overview of path planning methods are roadmap path planning, cell decomposition path planning, potential field path planning, and obstacle avoidance techniques. First, we will see the first method, roadmap path planning. In roadmap path planning, the environment is represented using a graph where nodes denote key locations and edges which defines traversable path. The various types of representations are visibility graphs, Voronoi diagrams, and probabilistic road maps. In this slide, we are seeing the diagrammatic representation of visibility graph for roadmap path planning. If you see in this visibility graph, if there is no obstacles exist between nodes, then nodes are connected by direct paths. The various nodes are start node, goal node, and obstacle corners. If you see this is the visible points, and if you want to find the shortest path between two nodes, you can find the shortest path using graph search algorithms. Now we move on to the next method, cell decomposition path planning. In cell decomposition path planning, it divides the environment into smaller manageable cells, and the types of cell decomposition or exact cell decomposition, approximate cell decomposition. Cell decomposition is otherwise called as grid-based decomposition. In cell decomposition, it divides the environment into smaller and manageable regions. You call it as cells. Each cell is marked as free space. See here, free space. Then occupied space are called as obstacles. Then you have blocked, that is obstacles are represented in black color. Here the robot navigates through adjacent free cells to reach the goal, and this method is mainly useful in structured environments like warehouses. If you see in this diagram, obstacles are marked as black and free spaces are represented as white, and the path will be from start node to goal node, and it moves through the free cells. The next one is potential field path planning. In potential field path planning, a robot is treated as a charged particles influenced by attractive and repulsive forces. You know, attractive means pulling. Attractive force pulls the robot towards the goal, and repulsive force pushes the robot away from obstacles. Now we will see the representation of potential field path planning. In potential field path planning, the robot is influenced by attractive forces pulling it towards the goal and repulsive forces pushing it away from the obstacles. The goal G attracting the robot, obstacles pushing the robot away, and the arrows indicates the direction of the movement. The next one is obstacle avoidance path planning. From the term obstacle itself, it's clear that if there are any obstacles, it will remove the obstacles and the robot moves through the free space. In obstacle avoidance, the robotics ensures that a robot navigates from a start position to a goal position while avoiding obstacles, and this is crucial for autonomous robots in dynamic environments like warehouses, self-driving cars, and robotic arms. The working procedure of obstacle avoidance path planning is: in path representation, the environment is divided into grid cells where each cell is either free space or an obstacle. The robot moves through free cells to reach its goal. The navigation logic behind this method is: the robot checks if the direct path to the goal is blocked. If an obstacle is detected, it chooses an alternative route. The robot follows arrows indicating movement towards the goal while avoiding obstacles. Now let us see the various case studies in path planning applications. The first one is autonomous vehicle navigation. The techniques used are roadmap and potential field methods, and the working procedure of this is: the vehicle creates a roadmap of its environment using GPS and sensor data. Either you can use visibility graphs or Voronoi diagrams, which helps to determine the shortest and safest path. And the potential field methods guides real-time movement where the destination attracts the vehicle while obstacle exert repelling forces, as we have seen already. Examples of autonomous vehicle navigations are self-driving cars, which uses lidar and AI-based decision making to avoid obstacles and optimize routes. Example is Tesla Autopilot. The next one is warehouse robotics. In warehouse robotics, the technique used is grid-based cell decomposition. The working process of warehouse robotics are: first, the warehouse is divided into a grid marking free spaces and obstacles. The robot moves through free cells while avoiding blocked areas. You can use any pathfinding algorithms, for example, A star algorithm, and you have various algorithms which ensure efficient navigation to optimize time and energy consumptions. Example of warehouse robotics is Amazon warehouse robots, which uses grid-based planning to pick and place items with high efficiency. The next one is medical robotics. In medical robotics, the techniques used is precision path planning. It works such as, for example, if you consider surgical robot, exact cell decomposition is used, which maps the human anatomy to avoid critical regions. Then you can use obstacle avoidance techniques, which ensure the robot's movements are precise and non-invasive. And next, motion planning considers real-time adjustment to ensure safety and accuracy. One of the example of medical robotics is Da Vinci surgical system, which uses robotic arms to perform delicate surgeries with minimal inversion. Thank you. In the next session, we will see the part 2 of Unit 4 Vision Systems. Thank you.